multiplied by our strain. Okay?
But their standard modulus of elasticities, right? Like it says steel is 29 million.
Yep.
Wood like 1 million.
Yep.
You know what I mean?
Yep. So, and again, what we'll have to keep in mind, just like with our allowable stress for concrete, your allowable modulus elasticity. Your modulus elasticity for concrete is going to directly depend on its strength. Okay? In fact, Braun Intertech and a number of other labs just got done doing a set of round robins through ASTM. We had a bunch of modulus elasticity data from the 1970s, and the size of buildings that they constructed in the 1970s are nothing at all like the size of buildings that we construct in 2018. In fact, we're getting a new world's tallest structure here in February in, no, in Saudi Arabia, I think. I think the Saudis are building it. The current one is in Dubai, isn't it?
Yeah.
But we're very interested in the stiffness of this material when we're talking about large vertical structures. We're also interested in our modulus elasticity when we're talking about bridges, how these things are flexing as we're loading them, okay? So, we can then also rearrange this if we need to determine length change, and that's just going to equal our loading condition times our initial length times our area times our modulus elasticity, as Russ said. Yeah, we can look this up in the chart. Okay?
And that's to find the delta?
That's to find your change in length.
Yeah.
Yep.
Okay.
Why would people be interested in knowing what change in length of material is going to be?
For expansion joints, like you said, right?
Yep. Not well, and not just for expansion joints, but
well, that's one of the reasons.
yep,
Right?
yep. So we know what size expansion material to put in. Think about the St. Croix crossing. Is it important to know the change in length of that concrete over time? We'd better know that, right? If we don't design enough into it, we may have too far of spacing in our joints. And if we don't allow space, what's going to happen? We have to keep in mind that St. Croix crossing is a bunch of box girders. Okay? So if those boxes expand too much over time, as Marshall said, they're going to push into each other and they're going to start buckling up into the roadway.
It's the same with concrete.
Yep. Yep. Yeah, and that's what we have to think of.
Like some like sidewalks, how they always are, they buckle up instead of down.
Yep. And do you think the taxpayers of Minnesota and Wisconsin will be excited about that? Probably not. They probably would not be really happy driving over that bridge if we weren't aware of what these effects are, okay? So the example question that you get in your textbook, it doesn't look like this marker is going to make it.
You and markers, man.
Yeah. I think this one will be good. So we'll call this example 6. So we have a 2-inch diameter steel rod. It's 10 foot in length. Oh my goodness. Guess we're riding blue until we die.
It'd be fun for the people online to read that.
What's that?
So it'd be fun for the people online to read that.
Yeah. We have a force of 60 kips. So, under this loading condition, how much elongation will occur? Okay. Which form of the equation do we need?
The delta.
We're trying to determine delta L. Okay? you see this? Okay. What is P?
60.
60 kips. What is L?
120 inches.
10 feet or 120 inches, okay?
Would you wanna do,
You're already doing in inches.
The diameter of our rod is in inches.
no, I'm saying would you wanna do 120 inches instead, or what?
I personally would. Hey, does it matter? Kyle, does it matter to you if you start out 10 feet? Kyle knows he's got 12 inches in a foot, so he's gonna build into his equation 12 inches per foot, right? Then his feet go away and now he's right back with where Rush is starting out in 120 inches. So yeah, either is fine from the purposes of this class. If you're given something in feet, I'm assuming that you all know how many inches are in a foot. I think that I'm safe in giving you all that benefit of a doubt, okay? I guess I should also say, now that I've shown you, also though, when you're dealing with square inches, to multiply by 12, or to multiply by 144, not 12, I'm also going to assume that you've got that down as well, okay? What about cross-sectional area?
3.14. So it's 1 inch square is 1 times pi is 3. So it's 1 times 3.14.
Okay. Yep.
3.1.
So, yeah, so Rush skipped ahead, and he said, okay, my diameter is 2 inches, so my radius is 1 inch. 2 divided by 1 is 1, I'm squaring that. And what's our modulus elasticity for steel? What did you say it was?
29 million.
29 million? Okay. So if we're operating this guy in PSI, what should we do with our kips?
Convert it?
Convert it to 60,000 pounds. Okay?
Is that pi times 1 squared?
That is pi times 1 squared. Sorry, I'm getting sloppy, John, aren't I?
No. No, you're not. You're good. But I do believe this is example 6 or example 4.
It's probably,
Four.
I think it's example 4 in your book. I had 2 other examples that I did previously to starting the examples in the book. So, yes, you have a good point.
While you were sledding.
Yeah.
Yeah, if you're playing the home version, you're on example 4 in the book, right? Okay? Are our dimensions going to work out on this? What should we want our delta L's units to be? We want it to be in inches, right? So we have to keep in mind, are we getting to inches?
Yes.
Are we?
Yes.
Kurt thinks so? Okay, we have square inches here, right? And those are in the denominator. And we have inches squared here. That would be in the numerator. So they go away, right? P in PSI is the same as pounds, right? So that goes away.
Leaves you with the 120.
If we started like Rush, we were at 120 inches. If we started like Kyle, we were at 10 feet and converted to inches. So we're left with inches in our units. So dimensionally we're correct. So now we can start doing our calculations. Okay?
It's 7.2 million divided by 91,118,000.
Yep. Is everybody all right with me not writing all of that up on the board?
Burn it, write it.
What's that?
Burn that marker out.
That's the online class, what they think.
Yeah.
There isn't instantaneous feedback yet. That's generation 1.2.
I hear all their books slamming shut and
Yeah.
going to the bar.
So our ultimate change in length ends up being, once we plug and chug on the numbers, 0.079 inches. Okay?
So again, I'm looking forward into the questions here.
Yep.
And the first one's having us solve for something different there. It's having us solve for the force. And I'm having a hard time putting this
Okay.
problem together, so
Yeah. Is everybody good if I erase this? And then we can look at how we'll manipulate this equation.
I came up with an answer, but it just doesn't seem to. I might have something wrong.
So, are you all right if I start with the E equals instead of the delta L equation? Or do you want
That's true, but you know, it's given us that it's
which
it's
question are
a
you looking
steel
at?
bar, A,
2.1A on
2.2A.
or
So, applied to a steel bar 1 inch square and 2 feet long, what's the force that you need for a .016 elongation? On page 56.
You're looking at A.
A, yeah.
Yeah.
So the issue might have been converting, no. I should've mentioned.
To a steel bar,
So it's a 1 inch square
1 inch square,
and it's 2 feet long.
and
And it, in order to produce an elongation of .016.
0.016 inch elongation.
So I had it set up just like the problem we did, and instead of being like where the 60,000 pounds is there, I had the X. So that's what we're trying to figure out, we're trying to figure out the force.
So you have delta L equals P times L AE,
True.
okay? And you're saying P equals X that you don't know.
Yeah,
Yep,
yeah.
okay?
So, you know, I set it up,
So how would you isolate P or X, however you're dealing with it? What would you want to do?
divide by.
Divide by
No.
Times, go first times by AE, then divide by L.
okay. So that would have probably been easier, because I wrote out the numbers first, and I just kind of got lost in the sauce. On how
Sure.
to set up my,
Yeah. And that's, I think Rush brings up a good point, is sorry, my recommendation would be, don't try and chase the numbers first. Okay? If you start trying to chase the numbers, we might forget that, you know, L equals 240 inches and E equals 29 million PSI. And maybe we divide that and you're like, oh man, now I don't remember where that goes. So my recommendation would be, and pick either format of the
24
equation.
24 inches, but
What's that? Oh yes, sir, 2 feet, yep.
so let's see if I did it right.
Start with either form of these equations that you feel comfortable with. Change around the variables, okay? Change around the symbols. Then start plugging things in, okay? Isolate your unknown, then solve with your known values, okay? Does that make sense?
So when it's saying 1 inch square, that's actually, it's a square beam.
We have a square,
Beam, it's not a,
yep, we have a square steel rod, 1 inch on all sides. Yep.
okay.
Stop getting lost in the sauce.
Hey,
You lost in that sauce, brother.
yeah, bro.
You could have gotten lost in the sauce yesterday.
Feel
It
free
was
to
a
use
snow
that,
day.
you know.
Getting lost in the sauce on a Tuesday is not a good idea,
Yeah,
right?
you guys have the wrong idea of sauce here.
Tuesday, Thursday, asshole.
Sauce would be this button.
No? Do I look hungover?
You always listen to show
I always look hungover.
Yeah, we can never tell.
That's his game. You know?
It's like I show up drunk every day. No one will know when I'm drunk.
Exactly.
That's all they know me by.
So E would be,
E would be
There's our
the
10-minute alarm.
Did you get that one
E's
solved, Rush?
modulus, so,
It's not right. Yeah, it is.
Okay?
so.
So,
So in that case, so
Yeah.
L is obviously the .016, right?
L,
No, like the delta
oh,
L,
I did it right.
right? Because that'd be the elongation.
yes,
19,333.
Yes.
And then A would be the
One.
1 inch square, right?
It's 1.
And then the E is
the E you'll pull out of the table.
Oh, okay, and then,
29.
oh, and then 2 foot long is the L.
Table 2.1 gives you modulus data for steel and concrete. Does it give you modulus data for timber? I don't think it does.
I think it actually gives you a range. It says one.
Oh, it does give you one for
It
for
varies
structural
from
ones.
something less
Got-
than 1 million to
got-
1.
What is the equation this all stems off of?
It's right there.
E equals P times L over H delta L?
So if you go for.
It all stems off of the ratio of, well, yeah, in the grand scheme of things, it comes off of Hooke's law. Which, I don't want us to go down the rabbit hole of that, that's physics 2 stuff. I don't want to, or it's physics 1 stuff, I don't want to spend a lot of time on it. But what it's saying is that the stiffness of a material is directly proportional to the force, to the stress applied,
I got it.
and inversely proportional to the strain. So if you take a ratio of what the stress is on that item and how much its length changes, that tells you how stiff it is, which makes sense, right? It's telling us that if we can, if we have 2 different materials and we apply the same stress to both of them, and they have different strains, the item with the larger modulus elasticity, so smaller strain, it deforms less, is the stiffer material. Okay? That, everything generates off of that. Okay, so we're rewriting our stress as our load divided by our area.
That's gonna
We're
be,
rewriting our strain.
point squared.
Oops, sorry, I
So you can
erased.
take that out. So it's
Erased?
point-
Erased.
that's
Good thing it's
29.
not an English class, right?
24.
Our strain we just rewrite as our change in length divided by our initial length. And then from there, then we're just doing algebraic manipulation. Okay? That's a good question, Joe.
So the force would be,
Are you talking about this
so,
specifically?
yeah, back into that,
Yep.
the force, since it's 19,000, we keep it in inches?
Your
So
force
would you-
is hopefully
would
in
you-
pounds.
So the answer, when you do that equation right there, you get 19,333.3, okay? So if you're gonna put it in pound, is that already in pounds?
Yes. Do the cancel.
Yeah. Because your modulus elasticity in 2.1.
Oh, is it?
Is in
Yeah,
PSI.
yeah, yeah. Okay, alright.
Now, you may be interested, Rush brings up a good point. If you don't want to use 29 million PSI, you may use 29,000 KSI.
And then,
Just keep in mind that your load, yeah, like Kurt said, your load will come out in kips. I'm fine either way, as long as you're dimensionally correct. Okay? Don't put PSI in here, not do any dimensional analysis and somehow come up with kips,
yeah,
right?
yeah.
Because it's not going to work that way. Okay?
Change is bad. Had a hard enough time getting over the kips and KSI.
It's 11:20. We're certainly not going to tackle method of joints.
So,
The last section that you have, well, I should say, we're not going to tackle it today.
so page 80 though, do you want us to
What's
put
that?
that on the assignment? You have it on the assignment.
I have it on the assignment, yep, and I'll get 2 posted. You can start on the first 2 items though, okay? We'll go over method of joints on Thursday. I want to say something on buckling. It would just take us about 1, maybe 2 minutes. You're not going to have any problems where you're calculating buckling, because we need to know things like the moment of inertia, the stiffness of the material, and it's just, we're going too far down the rabbit hole. I just want you to be aware that when we're talking about where the payoff is, it's not going to be in a footing, okay? It's not going to be in a 2-foot long rod. It's going to be when we're talking about columns in a building, okay? We're going to be interested in, from the scale of economy, we want those columns to be as narrow in cross-sectional area as they can be, right? Does that make sense to everybody, why we'd like to do that? We're using the least amount of material, okay? The problem with that is, when we're talking about columns, what type of axial load is being exerted on them? Compression
Compression,
or tension?
compression.
Compression, right? When we're compressing something and it's 4 inches in diameter and 8 inches tall, it's fairly easy to get it into pure compression. Okay? If we're talking about a column that is 8 inches in diameter and 10 feet long, 12 feet long, 15 feet long, what could end up happening?
Talking about,
We could tend to try and buckle it, right?
yeah, because it twists in different directions.
Yep. And there's actually 2 types of twisting. We'll talk about torsion as well, where torsion is actually trying to rotate it. Buckling, just be aware of what buckling is. Buckling is, we're going to have a member, and because it's very difficult to model pure compression, we may actually be compressing like this, and what's going to happen is we're going to change the shape of our column. And this is exaggerated for comedic effect, but if we get too much of this buckling, what happens to our column? It's going to blow out in that direction. Okay? So that is something that structural engineers look at. Okay? It's also known as eccentricity. Okay? But the term they actually use is relative slenderness, which not a lot of people use.
So-
Think of it as buckling.
So when you get those forces, like one maybe going up and one coming down, is that when you get the twist then? So like, let's say you get that
It could-
kind of arrow going.
It could be, yeah. Marshall brings up a good point, because what we're doing is we're working in 2 dimensions on this board, right? We're actually going to have portions of this column coming out of the board. We're going to have portions of the column going into the board. These forces are also going to be going into the board. So yeah, that's where you actually get torsion, where the column is actually going to try and twist around itself. Okay, so yeah, that's absolutely another force. We'll talk about that at a later point as well. Okay, so we got through 2.1, we got through 2.2 and 2.8 today. Okay, Wednesday we'll get into method of joints. We'll do the lab. I'll have these finished constructed tomorrow and some problems for you. We also have Molly. I forget what Molly's last name is.
Ringwald. I was gonna say the
No,
same thing.
no, not Molly Ringwald, no. She's a teacher in the architecture department. She's gonna come in, talk a little bit about what designers do. Okay?
Make my life.